need a name. What's my name? Today, I'm going to talk to you about potentials. Woohoo! So, the first thing I need to do is do some vector calculus. Uh-oh, where's my pen at? Ah, it's in my pocket. Hi, this is Matt, and I'm coming to you to talk to you about the electric potential. Okay, so let's start by thinking we already know that the divergence of E is equal to rho over epsilon naught. That is the differential form of Gauss's law. Okay, but we also want to ask the question, what the crap is the curl of E? What the crap is the curl of E? All right, so let's dive in. Remember that we can always think of the electrostatic field as the accumulation of electric field from point charges. So at its core, the electric field is just a principle of superposition of all of the point charges added up. So if I could prove that the curl of E for a single point charge is 0, then it would have to be 0 for every point charge. So remember that the point charge obeys Coulomb's law. 1 over 4 pi epsilon naught, the integral of Q over R squared, R hat. Sorry, there's no integral because I'm just taking the field from one charge. Basically, it has this form. 1 over R squared times some constant, I don't know, we'll call it gamma, why not, R hat. Right, so it goes as 1 over R squared times some factor times R hat. All right, so now if we take the curl of a vector in spherical coordinates, we have the following equation. Uh-oh, it's my handy-dandy textbook. And I look it up in spherical coordinates, and it is actually pretty scary. The derivative with respect to theta, sine theta, v phi, minus dv theta d phi, and all that points in the r hat direction. But then I also have two more terms. So plus 1 over r, the sine of theta, or sorry, these aren't v, these are e's, right? Because that's the vector I'm putting in there. So 1 over sine theta here. And then I have d er d phi. Oh, sorry. And then minus ddr r e phi. And this points in the theta hat direction. And then there's one more term in the phi hat direction. Plus 1 over r ddr r e theta minus der d theta. That's a parentheses there. Phi hat. So basically what I did was I took the curl and spherical coordinates right out of the textbook and I wrote it down there, right? It's a giant gobbledygook of mess. But if I look at what I know my electric field should depend on, it only depends on one component of the vector, namely the ER component. So E theta and E phi are 0. So everywhere I see those, I can just make those terms 0. So this whole term here goes to 0 because there's no ER in it. Right? That whole term goes to 0. And if I look at this term's going to go to 0 because there's no ER. The E phi term is 0. So this term goes to 0. And if I look at this one here, this term here is going to go to 0. Okay, so all those terms go to 0 because there's only a component in the R direction. And now we have to think about what these partials would be. This partial is with respect to phi, and that partial is with respect to theta. But if I look at how E is defined, it's only defined as a function of the variable R. So both of these terms must go to 0. And I'm left with the curl of E has to equal 0 for a point charge. Now that sets off a set of mathematical beautifulness that you remember from Physics 1 and methods that should just make you super happy, right? When I know that the curl of a vector is 0, I know what about it? I know that that vector field is conservative. Woohoo! Right? And if I know that it's conservative, I know that I can write down a scalar that's only path independent and only depends on the endpoint and the endpoints of the path that I'm going. Right? So if I take this, curl of a vector field gives me 0, I know that that vector field is conservative, and I can write down a scalar field. I can write down the following equation. That E is equal to minus the gradient of V, where V is a scalar. Okay, let's prove it. So first thing, let's look at Gauss's law. I know that the divergence of E is equal to rho over epsilon naught. So if I take this puppy and I plug it in there for E, you get that the divergence of del E is equal to, V, is equal to rho over epsilon naught. Of course, that's going to make that negative because there's a negative here. And if I look at this thing, hey, that's just the Laplacian, right? Del dot del is the Laplacian. So this becomes the Laplacian of V equals minus rho over epsilon naught. All right, that's cool. That tells me about V. Good. What else do I know? What about, I know that the curl of E has to equal 0. So let's prove it. Make sure that this formalism will actually give me 0. So I take this and I plug it in, and I get the curl of del acting on the potential has to equal 0. So how would I prove that? Well, if I take I, j, k, dx, dy, dz, dx, dy, dz, and act that all on V, what do I get? Well, if I just look at the I hat terms, and I come down here, you get dy, dz. And then, going that way, I get minus dz, dy. And all that's got to act on V. Now, there's going to be a j hat term and a k hat term, but let's just worry about the I hat for a second. Okay. How do partials work? Well, when I take the partial of something with respect to y, I hold the z constant, right? I hold the x constant as well. The only thing I don't hold constant is the y. which I take the partial of. So this term here, according to that, it's a constant. And so if I know I have a constant, I can just pull it out of the derivative. So this becomes I hat dz dy minus dz dy, acting on v, of course, plus plus plus. And this term goes away. It's 0. Now it's going to do that in the y direction. It's going to do that in the z direction as well. So that results in 0. So being able to write this as a scalar, e as a scalar, was okay because the curl of the vector equals 0. You bet I'm going to ask you to do this on a test at some point. I have probably about half the years that I've taught this class. This is a really big thing. The electric field is a conservative field, right? Just like the gravitational force is conservative, for actually the exact same reason, the electrostatics force is conservative. And we can write that field in terms of a scalar that's path independent. And this is huge, right? Because just like the same way I could use the potential energy, now I can use the electric potential. Now, there's a lot here. There's a lot to unpack. So, F, the force, is equal to QE, right? And U is QV, where Q is the charge that's interacting with the field. U is the potential energy. And V is the electric potential. Now, this is one of those times where I wish I could go back, find the people who came up with physics, and like bop them on the head. Bop! Here, let me show you what that would look like. Whoa! I just invented physics! I'm going to call that the potential energy. And I'm going to call that the electric potential. Bop! Right? They're terrible names for this, right? Because what inevitably happens is we drop the energy when we want to use slang, and we just call that the potential. And when we're working with V, we just want to drop that, and we're going to shorthand that by calling that the potential. So now we got a problem. So we've got two things that we both call the potential that are directly related, but they're different. The SI units here are joules, and the SI here are volts, right? Volts. You just got to get used to this, and because we all do it, myself included. Okay, so if I can write down that I have a vector is equal to the minus gradient of a scalar, I can do the inverse of this operation, right? Which turns into fundamental theorem of calculus, which is that this becomes VB minus VA equal to minus the integral from A to B of E dot dl, where this is the path, right? And it only depends on the endpoints B and A. So this can be proved by taking this and plugging it in and applying the fundamental theorem of calculus.